Hello students, welcome back to CLARI Concepts, Unleashing Conceptual Learning. For more lectures on conceptual clarity, you can log into our website clariconcepts.com. Today in this lecture, we are going to talk about one of the really important device in fluid mechanics which is used heavily in the industries to measure flow rate of the fluid. So before I move on to that particular device, I would like to ask you several questions. So let us say, for example, the tap that you use at your residential houses, right? If I ask you that when you open the tap, the water start coming out of it, right? What is the flow rate of this water? What is the flow rate of this water? Can you calculate this or can you measure this? Pause the video, think about it. Now, first, I hope you are aware that what is the meaning of flow rate, right? What do you mean by flow rate? Flow rate means that how much amount of water is coming out through this particular tap in 1 second. Again, I am repeating. So that means you can say that from any section, let's say this is the section 1-1. So how much amount of water is crossing this section in 1 second? Amount can be calculated based on mass as well as volume. So if you calculate how much mass of water is flowing through this section in 1 second, that will give you mass flow rate in kgs per second. And if you calculate how much volume of water is flowing through this particular section every second, that is said to be the volume flow rate, that is in meter cube per second. Now my question is, how do you measure that? How will you make sure that how much quantity of water is flowing through this section, or rather how much quantity of water is coming out through this tap in every second? Alright, let me give you an experiment today. Now, let us say, for example, you can easily do this experiment at your house. What you have to do is you take a bottle of non-volume. Let us say volume of this bottle is, for example, 1 liters. And I hope at this point of time you are aware about how do you convert liter into meter cube. Okay. So, if you want to convert liter into meter cube, you need to divide the value by a factor called 1000, isn't it? To convert it into meter cube. So, volume is how much? 0.001 meter cube. So this is the volume of this bottle. It is empty, entirely empty. Now what do? You have take a stopwatch in your hand, open the cap of this bottle, you just place the bottle underneath of this tap and start the stopwatch. And then stop the stopwatch till it is completely filled. This means what? Let us say, for example, time taken in this particular experiment or time taken for water to fill the entire bottle is, let's say, 10 seconds, for example. How much? 10 seconds. So now what is the flow rate? Now you see, what does it mean? It means that 0.001 meter cube of water has came out of this particular tap in 10 seconds. Now your question is, you want to find how much water has came out of this in 1 second. So can you say this is 1/10 of this? So how will you calculate flow rate? Q will be equals to volume divided by time. Volume is 0.001, time is 10 seconds. So this is 0.3 times 0 and 1 meter cube per second. If you want to talk in liters, you multiply it by 1000. This will be, if you multiply it by 1000, you will get 0.1 liters per second. And for water, this 1 liter is also equals to 1 kg because density is 1000 kg per meter cube. So you can say this is 0.1 kg per second. This is mass flow rate. Now what does it mean, all these things? You see, it means that you have calculated practically the flow rate of the water flowing through this particular tap. Yes or no? By placing a vessel of non-volume and measuring time taken to fill that vessel. Another question for you. Now tell me, all these industries, process industry, power industry, they are all equipped with a pipe network through which a fluid is flowing. So let us say, for example, this is a pipe that is of your focus. Now if I ask you a question that now can you measure the flow rate of the water or any fluid flowing through this pipe from any section? Can you measure this? Now you cannot cut the pipe and put the vessel at the discharge, right, to measure the flow rate. So, and many a times the end output may not be into your access also, because the process that this industry is following, it is going to the boiler or let's say condenser. So you need not to have the kind of vessels and measure the flow rate. Now how do you measure the flow rate of water flowing or any fluid flowing through the pipes in real time? The device that is used to do that is called Venturimeter. So today in this lecture, we will be talking about this device called Venturimeter. So I request you to please pay a close attention. This is a really very important lecture. Okay, so let's say this is a pipe through which a fluid is flowing, and you would like to measure the flow rate of the fluid flowing through this pipe. So simple, mount the Venturimeter. What is Venturimeter? It is simply this kind of device. You can see Venturimeter is a device which has a converging section first, which is called convergent section, then a constant diameter section which has smaller diameter, which is called throat, and then diverging section. Now in 3-dimensional it is like funnel shape. You can see it is 3-dimensional body. Now what do? You cut this pipe and you remove this center portion and then mount this at this particular place. Now you will be amazed, how does changing in cross sectional area will give you the flow rate. Let me show you the derivation and the formula how it will give. You can see these spots, right, 1 and 2. These spots are used to measure the pressures at these sections. Now we'll see how will this device, wherein simply you have changed the area, will help us in measuring the flow rate. Let us see that. So we will derive the final form of that. So the sectional view of Venturimeter looks like this. So this is your main pipe. This is also a main pipe, and in between the main pipe you have taken a section, you have inserted the section called Venturimeter. As I said, Venturimeter is converging cone, then constant throat, and then diverging cone. Okay, and the ports that you were seeing, in order to measure the pressure difference between the the main pipe and the throat, a U-tube manometer is connected. I hope you are aware about U-tube manometer. If you are not, you go back to my lecture where I have explained that. And there is a manometric fluid which is heavier than the fluid flowing through the main pipe, okay, which is used to calculate the pressure difference. Now if I simply talk about several things, this is upstream of the Venturimeter. So water is flowing from left to right. This is downstream, and this section is called Venturimeter. Entire geometry is called the Venturimeter. So let us suppose this is density of the manometric fluid rho m. Density of the fluid flowing through the pipe is rho f. Okay. Diameter of the main pipe that comes is, let's say, capital D1 for example. Diameter of throat, let's say, I'll not put small d, I will say this is capital D. So this diameter is capital D2 for example, right? So I'll mark this as section 1 and this throat as section number 2. Clear? Now see, let me try to use the Bernoulli's theorem, and let me say that you can say the datum line is somewhere over here, datum line. Datum line is anywhere in between, so you can say that the section 1 center is over here. So this is your Z1 from here to here, and then this is your Z2. So this is the same center, right? Same distance. So you say Z2. So Z1, Z2 will be equal, right? Both of them will be equal because the pipe is said to be horizontal. So let me now apply Bernoulli's theorem between section 1 and 2. So when I do that, I will get P1 by rho g plus V1 square by 2g plus Z1 should be equals to P2 by rho g plus V2 square by 2g plus Z2. Now since Z1 and Z2 are equal, you can cancel them from both the sides. Now in this equation, if your objective is to find the velocity either in section 1 or either in section 2. Why? Because you want to know the flow rate, and I hope you are aware that flow rate Q is basically either area 1 into velocity 1, or this is also equals to area 2 into velocity 2. They are the same. So if you can get V1, that is velocity at section 1 in the main pipe, then you can multiply that with the cross sectional area of the main pipe, that is pi by 4 d1 square, to get the flow rate. And if you get this V2, that is velocity at the throat, then you can multiply with that particular area to get the flow rate. The product will be same, obviously, right, because the flow is steady and there is nothing coming out of this particular geometry. So now your objective is to find either V1 or V2. So let me just put down the equation. So I will take V2 square minus V1 square by 2g. So I will take this V1 square on the left hand side, this will become minus, and then P2 on the P2 on the left hand side, V1 on the right hand side. So if you reassemble the equation, you will get V2 minus V1 square by 2g and then P1 minus P2 by rho g, because denominator are same for both those terms. Now g will get cancelled. You can take V2 square minus V1 square equals to P1 minus P2 into 2 divided by rho. Now when I say rho this means what? Rho of the fluid flowing through the pipe, because you are talking about the section 1 and section 2. So section 1 has the fluid of density rho f, the main fluid flowing through the pipe. Remember this, because there are two fluids. One is the main fluid, one is manometric fluid. So don't get confused. This rho is for the main fluid, rho f. Okay, rho f, I'll put rho f. Now in this equation, if somehow, let's say, I'll put this equation number 1. If somehow I get the pressure difference between section 1 and 2, then I know the one equation which is in V1 and V2, because rho f will be known to me, because the fluid flowing through the pipe, I must know it is water or air. So density will be available with me. Now this is one equation where V1 and V2, there are two unknown variables. Now if I get another equation where V1 and V2 are V1 and V2, then I can say that this is I have two equation, two unknown to get the answer. Now from where will you get that equation? Okay, but before going to that, let me say that P1 minus P2 can be easily measured using the Venturimeter, YouTube manometer. That is the reason why we have kept the manometer, right? So P1 minus P2, first we will measure that, and then we will find another equation in which V1, V2 will be unknown. So then we will have two equation and two unknowns. So let us first mark some points. Let's say at this point, section 1 is there, this is section 2, right? So if I come down to this particular point, let's say 3, and then straight, this is number 4, this is number 5, and for an instance, this distance from here to here, let's say this is your some distance x, for example. Now what will happen? I want to know the pressure difference, so I hope you have gone through my YouTube manometers lecture. So when we will go from 1 to 2, I will try to see what is the difference in the pressure and all, right? So when I am at 1, pressure is P1. When you are moving down 2.3, so from 1 to 3, you are coming down. That means you are increasing the pressure. How much? Rho g h. What is the rho? Rho is the rho of the rho f g, and what is h? X plus hm. So this P1 plus rho f g x plus hm, right? Then you are at 3. When you move from 3 to 4, no change in pressure, because both the points are on the same horizontal line and they can be connected by the continuous line being in the same constant density fluid. Still, if you are not aware about how this is equal, you can look back to my previous lectures. Then you are moving from 4 to 5, you are going upward, so pressure will reduce. How much? Rho g h, which is the rho m, because in between 4 and 5 the manometric fluid is filled. So rho m g hm minus rho m g hm. Then again you move from 5 to 2, you are reducing the pressure, so minus how much? Rho g h, which is the rho of the fluid. Rho f, g and h will be the x. So minus rho f g x equals to what? At this point you will say pressure is P2. You want P1 minus P2, so you take P2 on the left hand side. So P1 minus P2, and if you open up this bracket, so plus rho f g x plus rho f g hm minus rho m g hm minus rho f g x equals to 0. So plus rho f g x and minus rho f g x will get cancelled. You are left with two terms. If you take these two terms on the right hand side, you will get P1 minus P2. P1 minus P2 will be equals to, when you take this to the right hand side, this will become plus, this will become minus. So when this is plus, you can take g common from both the sides, g and hm, sorry. G hm is common, this will be plus. So you can say rho m minus rho f in bracket g hm is the pressure difference, isn't it? Now you put this over here. So what you will get? You will get V2 square minus V1 square is equals to 2 divided by rho f, and there was P1 minus P2. P1 2 by rho f, P1 minus P2. P1 minus P2 is this, rho m minus rho f into GHM. Rho m minus rho f into GHM. Okay. So now if you look at this equation, the only unknown part, because you will be available with HM, you can measure it very easily using a linear scale. You know what is the difference in the density of the fluids. This is rho f, this is rho m, right? Rho m and rho f. So now the only way is if you can get another equation wherein you have V1, V2 as unknown. The another equation is what? Let's say this is equation number 2. You know that Q1 is equals to Q2. That means A1 V1 is equals to A2 V2. That means let's say V1 is equals to V1 is equals to A2 by A1 into V2. So V1 is equals to pi by 4 D2 square divided by pi by 4 D1 square into V2. This pi by 4 is cancelled. Now if you want V1 square, this is what? This you can say that D2, or let me not just go and put all this value right now. We will do it in the final form just to make, to keep it very simple right now. Okay, so if I want the square now, so what will I do? Let's say V1 square will be equals to A2 square by A1 square into V2 square. Now put this V1 in this equation. In equation 2, what you will get? You see, you will get V2 square minus, V1 square is this, minus A2 square by A1 square into V2 square equals to 2 by rho f, rho m minus rho f into GHM. So now if you further solve this equation, you will get, you can take V2 common and out. So V2 square 1 minus A2 square by A1 square equals to 2 rho m minus rho f into GHM divided by rho f. Now if you just take, if you can multiply it over here, you can write it like this, V2 square equals into A1 square minus A2 square divided by A1 square, whole square. So A1 square minus A2 square by A1 square is equals to, you can individually supply this rho f at both these terms. So this will be 2 GHM into rho m by rho f minus 1, because rho f by rho f is 1, isn't it? So now you can take this on the right hand side, you will get A1 square in the numerator, A1 square minus A2 square in the denominator. So V2 square will be equals to what? A1 square into 2 GHM rho m by rho f minus 1 upon A1 square minus A2 square. Now what is V2? V2 will be equals to under root of all this, under root of A1 square 2 GHM rho m by rho f minus 1 over A1 square minus A2 square, right? Let me just redistribute this equation again. So V2 will be equals to, see if you look at this equation, this is your under root of A1 square. So you can take A1 outside, it will be A1, under root of A1 square is just A1, right? So you can take A1 outside in bracket 2GHM, sorry, this is not rho f, this is HM, 2GHM in bracket rho m by rho f minus 1 over A1 square minus A2 square. Now this is not the final form, your purpose was to find the flow rate, that is Q. Now if V2 is received, you can write V2 will be equals to A2 into V2. So then A2 will be as it is. What is V2? A1 and all this term. So we will write A1 in bracket 2GHM rho m by rho f minus 1 over A1 square minus A2 square, isn't it? Now see what is this? If I can rearrange these terms, I can say this is, now whatever equation you have got, where A2 is the cross-sectional area at throat, this is D2, right? So this is your A2 will be pi by 4 D2 square. This is your D1, so what is A1? Pi by 4 D1 square. HM will be the difference in manometric level. Rho m density of the manometric fluid, rho f density of the main fluid, then A1, A2 again you are aware with, right, and G you are known. So everything is known to you now from this. You can calculate the flow rate. My question is, whenever you calculate the flow rate using the equation, do you think it will be always right? Question is, there will be some error associated with it. Why? Because you have derived this equation based on the theoretical fundamentals, that is Bernoulli's equation. And Bernoulli's theorem itself has some assumptions like flow is steady, flow is incompressible, flow is inviscid. In reality, the real flow will deviate from that particular assumptions, right? So there will always be some sort of error associated with that. So this flow rate is known as theoretical flow rate, QTH. Theoretical flow rate. So now question is, how do you get the actual flow rate? You can multiply theoretical flow rate with a factor called coefficient of discharge, CD, to get the actual flow rate. The CD will be given to you by the manufacturers and designers. They will, and they have an experimental setup to find the value of CD, right, the errors. So CD mostly for Venturimeter lies in between around 0.95 to 0.9899, right, almost. So then your Q actual will become CD into A1, A2, where CD is coefficient of discharge. In bracket, I will just simplify the equation 2G H upon A1 square minus A2 square, right? And what is H? I am putting the value of H, where H is equals to this particular term, that is HM into rho m by rho f minus 1. See why I am putting this like this, because this is the final form. The reason is that many a times what they do is they directly mount the pressure gauge rather than manometer. So they will say that P1 is pressure gauge over here and then P2 is pressure over here. So when pressure gauges directly are mounted, you get the values of pressure, you don't get this HM. In that case, this H, you can use the same formula, but then H will be what? H will be P1 minus P2 by rho Fg. You can see why this is the case. If I look at this expression, I will say how this came. Can I say H equals to, from H is basically the HM into rho m by rho f minus g, right? So if I look it like this, I can say rho m minus rho f and then HM divided by rho f. This is the same equation, right? If I put g on both these sides, what I will get? Rho m minus rho f HM into g, right? This is what, if I look at the previous equation, what is P1 minus P2? You might have got P1 minus P2 is what? Rho m minus rho f into g HM. So this is what? Rho m minus rho f into g HM. So numerator will become P1 minus P2 and denominator is as it is rho f by g. So therefore this is fine. So you can use both of this. So when manometer is given to you, then you can use H as this. When pressure gauges are given to you, you can use H as particular P1 minus P2 by rho Fg. So this is the final formula through which you can find the flow rate of the Venturimeter. I hope you understood this. I will show you some of the real pictures of Venturimeter. You can see the Venturimeters mounted in the industrial areas. Here is the throat, this is the throat, and there are two tappings you can see for the pressures, right? Two tappings, 1 and 2. Similarly, you can see one of the another Venturimeter. There are two pressure tappings and the fluid is flowing from right to left. You can see the convergent portion, the constant throat and then the divergent portion. So they are using it in the industry to calculate the flow rate. Thank you so much. See you in the next class where we will look into more of the fundamental of engineering concepts. Thank you.